Lesson 3 in Chapter 11 brings us to Newton's third law of motion. It can be found on page 323 in your textbook. Our objective today is to identify the relationship between the forces that objects exert on each other. Action and reaction. Newton's first two laws of motion explain how the motion of a single object changes. If the force acting on an object are balanced, the object will remain at rest or stay in motion with constant velocity. If the forces are unbalanced, the object will accelerate in the direction of the net force. That's the first law and second law. Newton's second law tells how to calculate the acceleration or change in motion of an object if the net force acting on it is known. Newton's third law describes something else that happens when objects exert a force on another object. Suppose you push on a wall. It may surprise you to learn that if you push on a wall, the wall pushes on you. According to Newton's third law of motion, forces always act in equal but opposite pairs. Another way of saying this is for every action there is an equal but opposite reaction. This means that when you push on a wall, the wall pushes back on you with force equal in strength to the force that you exerted. When an object exerts a force on another object, the second object exerts the same size force on the first object as shown in Figure 13. Figure 13, you have the car that is up on this hydraulic lift. The car is pushing down because of gravity and the weight of the car, but the force on the jack exerts exactly the same to hold that car in that position. So Newton's third law, force always come in pairs. There's an equal and opposite force. You push on the wall pushes back on you. Here's a couple other examples. After a gun is fired, there's a recoil. The gun comes backwards because there's an explosion inside the barrel that pushes the bullet forward. The reaction of you walking, you push up and forward to move forward, and the floor pushes back and down on your foot. Or another example to see this in action, because sometimes when you're walking you don't necessarily feel or see that the floor is pushing on you. If you're getting out of a boat, you push on the boat, because the boat is in water, it actually will move away from you, but the boat pushes back on you so it can propel you to move forward onto the dock in this example. Action and reaction forces do not cancel. The forces exerted by two objects on each other are often called an action-reaction force pair. Either force can be considered the action force or the reaction force. You might think that because action-reaction forces are equal and opposite that they cancel. However, action and reaction forces pairs don't cancel because they act on different objects. Forces can only cancel if they act on the same object. For example, imagine you're driving a bumper car and are about to bump a friend in another car, as shown in Figure 14. When the two cars collide, your car pushes on the other car. By Newton's third law, that car pushes on your car with the same force, but in the opposite direction. This force causes you to slow down. One force of the action-reaction force is exerted on your friend's car, and the other force is exerted on your car. So because it's happening on two different cars, they don't cancel each other. Another example of an action-reaction pair is shown in Figure 15. Here you see the little child jumping into the pool, pushing off of the ledge. The ledge is pushing back on there. That propels them forward. Because the forces are acting on different objects, they don't cancel each other, and there's motion that happens as a result. You constantly use action-reaction force pairs as you move about. When you jump, you push down on the ground pushes up on you. It is the upward force that pushes you into the air. Figure 16 shows some examples of how Newton's law is demonstrated in different sporting events. If you look here, there's an example that's zoomed in. When a tennis ball hits a racket, the tennis ball actually changes its shape because its force is going into the racket. The racket actually changes its shape and pushes back on the tennis ball, which propels this back to the other side of the court. In Figure 16, you've got somebody who's diving into the pool. You're showing that they're pushing off on the diving board, and the diving board pushes back on them. You've got Tiger Woods that is hitting a golf ball. The motion of that golf club hits the ball and moves it forward. The golf ball hits the golf club, and the golf club pushes the ball. You've got somebody here in gymnastics that is showing that they're pushing on the bar and the bar is pushing back on them. Another example that happens in nature are birds. Birds and other flying creatures also use Newton's third law. When a bird flies, its wings push in a downward and backward direction. This pushes air downward and backward. By Newton's third law, the air pushes back on the bird in the opposite direction, upward and forward. This force keeps the bird in the air and propels it forward. To visualize this, again, all three of these laws are described in Figure 16 on page 325. Newton's first law, according to Newton's first law, the diver does not move in a straight line because constant speed because of the force of gravity. This person pushes off of here and then pushes back, but then the first law causes this reaction and this movement to go in this curved form rather than to go straight up and straight down. The second law is shown as Tiger Woods, one of the greatest golfers of all time. He hits a golf ball, he applies a force that will drive the ball in the direction of that force. This is an example of Newton's second law. But the third law can be found here as well because the golf ball pushes on the golf club and the golf club pushes on the ball. And lastly, you've got Simone Biles, the recent gold medalist, one of the best gymnasts in U.S. history. Example of the third law would be applied when even objects don't move. Here, a gymnast pushes down on the bars, and the bars push back on the gymnast with an equal force. A lot of times on a balance beam or on horizontal bars or on uneven bars, the gymnast is holding themselves in a position. Just because that's happening doesn't mean that the third law isn't being applied, because the balance beam is pushing back on Simone Biles or the bars are pushing back on Simone Biles. In those examples, you have the third law being applied as well. Change in motion depends on mass. Often you might not notice the effects of the forces in an action-reaction pair. This can help if one of the objects involved in is much more massive than the other. Then the mass object might seem to remain motionless when one of the action-reaction forces acts on it. For example, when you walk forward, as in figure 17, you push backward on the ground. Earth then pushes you forward with the same size and force. Because Earth's mass is so large, the force you exert causes Earth to have an extremely small acceleration. This acceleration is so small that Earth's change in motion is undetectable as you walk. This picture kind of shows what that represents. The mass of Earth is actually equal to Mars, Venus, and the moons that are on those planets. Because mass of Earth is so large, when we push on Earth, technically Earth pushes back. And when we jump, that movement, that force doesn't actually move Earth because Earth is so massive. Technically it does, but it's not going to represent or show that because of the size of the mass that Earth has. A rocket launch. The launching of a space shuttle is a spectacular example of Newton's third law. 3 rocket engines supply the force called thrust that lifts the rocket. When the rocket fuel is ignited, a hot gas is produced. The gas molecules collide with the inside of the engine, as shown in figure 18. As these collisions occur, the engine pushes the hot gases downward. According to Newton's third law of motion, the hot gases push upward on the engine. The upward force exerted by the gas in the rocket propels the rocket upward. Weightlessness and measuring weight. We're on page 327. You might have seen pictures of astronauts floating inside a space shuttle or as it orbits Earth. Here's an example. The astronauts are said to be weightless, as if Earth's gravity were no longer pulling on them, yet the force of gravity on the shuttle is almost 90% as large as Earth's surface. Newton's law of motion can explain why the astronauts float as if there were no forces acting on them. Think about how you measure your weight. When you stand on a scale, your weight pushes down on the scale. This causes the scale pointer to point to your weight. At the same time, by Newton's third law, the scale pushes up on you with a force equal to your weight, as shown in figure 19. This force balances the downward pull of gravity on you. Well, free fall and weightlessness. Now suppose you were standing on a scale in an elevator that is falling, as shown in figure 19. A falling object in free fall when the only force acting on the object is gravity. Inside the free-falling elevator, you and the scale are both in free fall. Because the only force acting on you is gravity, the scale no longer is pushing up on you. According to Newton's third law, you no longer push down on the scale, so the scale pointer says 0. It might seem like you're weightless. Weightlessness is the condition that occurs in free fall when the weight of an object seems to be 0. However, you are not really weightless in free fall because Earth is still pulling down on you. With nothing to push up on you, such as your chair, you would have no sensation of weight. This picture shows an airplane that's called the Vomit Comet that astronauts use to train for this weightlessness before they actually go into space. So they've got to learn how to kind of be in equilibrium and control their body while they're in this weightlessness in space. To prepare for that, they get on this airplane that flies in this really distinct pattern. It goes up almost straight, and it levels out, and then it dives. And when it's diving, everything inside the plane is actually free falling, so you experience what it's like to be weightless because nothing's pushing on you, you're not pushing on anything. You technically have this weightlessness that is occurring. That helps astronauts prepare for what that's actually going to be like when they're in orbit, because when they're in orbit, they're technically in a free fall around the Earth, but because the Earth is curved and they're moving so fast that they are constantly in this free fall state. To understand how objects move in orbit, in the orbiting space shuttle, imagine that you were holding a ball in the free-falling elevator. If you let the ball go, the position of the ball relative to you and the elevator wouldn't change because you and the ball and the elevator are moving all at the same speed. However, suppose you give the ball a gentle push downward. While you are pushing the ball, this downward force adds to the downward force of gravity. According to Newton's second law, the acceleration of the ball increases. So while you're pushing, the acceleration of the ball is greater than the acceleration of both you and the elevator. This causes the ball to speed up relative to you and the elevator. If it speeds up, it continues moving faster than you and the elevator, and it drifts downward until it hits the elevator floor. When the space shuttle orbits Earth, the shuttle and all the objects in it are in a free fall. They are falling in a curved path around the Earth instead of falling straight downward. As a result, objects in the shuttle appear to be weightless, and they float, as shown in Figure 20. A small push causes an object to drift away, just as the small downward push on the ball in the free-falling elevator causes it to drift to the floor. If you want to look more into this, there's many videos on YouTube of astronauts who are in space that have shown what weightlessness looks like. One of the really cool ones is an astronaut wringing out a rag that's full of water. Because there isn't gravity, the water doesn't fall out of the rag. It just kind of like goes on his hands, and it kind of encompasses that entire area. Because the Newton's orbital canon shows here that if something is orbiting, it's technically free falling, but because Earth is curved, it falls in that orbit. Therefore, it creates and continues that sensation of weightlessness the entire time. That wraps up our reading and brings us to our reinforcement for today. Top of the page, the directions say complete the table by naming the action and reaction force in the following examples. You got a flying bird, action and reaction force, 2 bumper cars, action and reaction force, holding your hand out the window of a moving car, what are you pushing on, what is pushing on your hand, when you're walking, and the 5th one, touching your finger to your finger touches your nose touches your finger, they push back on each other. A number of those examples were found right in our reading for today, so you could identify the action and reaction force. And then the last portion here, you've got 6 through 10, it says complete the following sentences using the correct term or phrase, fill in the blank. And number 11, how could the action force of a canoe moving through water be increased? Well, why do you think you have a paddle while you're going through water? You push on the water pushes on you, and that motion takes place. Hope that helps you to complete your homework assignment. God's blessings.